All right, so in this section of Chapter 3, we're looking at the atom, and we want to explain the law of conservation of mass, the law of definite proportions, and the law of multiple proportions. We want to be able to summarize the 5 essential points of Dalton's atomic theory, and we want to be able to explain the relationship between Dalton's atomic theory and the law of conservation of mass, the law of definite proportions, and the law of multiple proportions. So this is not going to be problem driven. Again, the chapters are going to go back and forth, but there is conceptual issues here, and you guys need to make sure that you understand the concepts and that you are able to explain the concepts. So when we talk about the atomic theory, we're ultimately going to be looking at the history of how science began to and now does understand or models the atom, what the atom is, what it's made out of, how it interacts, all of those types of things. And this is a foundational topic to any study of chemistry. So the transformation of a substance or substances into one or more new substances is known as a chemical reaction. That should be review. We covered that earlier last week. Okay, chemical reaction means, we define a chemical reaction by the fact that you're moving from one substance to a completely new or different substance. In terms of that happening, we have within science the law of conservation of mass, which basically states that when this is happening, when a chemical reaction takes place, when you combine hydrogen and oxygen to get water, when you combine sodium and chlorine to get sodium chloride or salt, when that is happening, mass is neither created nor destroyed. Okay? Under ordinary chemical reactions or ordinary physical changes, mass is neither created nor destroyed. What that means then, that conceptually begins us down the road to say there are theoretical math concepts that we can apply to equations. The mass of my reactants should always equal the mass of my products. That's what this is saying. However many grams of hydrogen and however many grams of oxygen I put together should equal the total grams of water on the other side. Okay? And this is where we're going to start talking about moles, molecular weights, and things like that, because when we do this, the math theoretically, we've got to understand, we've got to be able to use the concepts of moles to do these equations, and we'll get to that. But the idea, the concept here, guys, is the mass of what I start with is the same as the mass of what I end with. Mass is neither created nor destroyed. We also have the law of definite proportions, which is going to play into what I'm discussing here about mass on both sides being equal in moles, okay? A chemical compound contains the same elements in exactly the same proportions by mass, regardless of the size of the sample or the source of the compound. Again, the law of definite proportions says this: a chemical compound contains the same elements in exactly the same proportions by mass, regardless of the size of the sample or the source of the compound. So it's always going to be the same. When we go to the law of multiple proportions, what we're saying, if two or more different compounds are composed of the same two elements, then the ratio of the masses of the second element combined with a certain mass of the first element is always a ratio of small whole numbers. Now, the hard thing here, guys, is that when we look at these in terms of definition, it seems pretty complex. But what we're saying is that there are mathematical functions that come out of the law of conservation of mass. The fact that the mass that you put in is the same mass that you get out. What we're starting to derive out of this is that there are mathematical concepts that come from that. Okay, because what we're saying is to talk about mass is to talk about the number of atoms. Okay, and those things should always be the same. That's what we're talking about. To talk about mass is really to talk about the number of atoms, and so what we're saying is you can talk about this in mass, and the mass on one side should always be equal to the mass on the other. The mass of what you put in should always be equal to the mass of what you get out, but ultimately what that is a discussion of the number of atoms, and that's where we get these idea of proportions. So let's take a look at this diagram here that can show this. If you have hydrogen and oxygen and you put them together, you get water. Okay. So what we're saying here, if you look at this, is that 3.348 times 10 to the negative 27 kilograms of hydrogen, that's how many kilograms of 2 hydrogen atoms there are, plus 2.657 times 10 to the negative 26 kilograms of oxygen gives you 2.992 times 10 to the negative 26 kilograms of water. Now, why is that if the mass is supposed to be the same? Well, you have your laws of proportions. And really what this ends up being when we see this done is that hydrogen plus half of oxygen equals H2O. And you can see this with each one of these as you look at these examples. So when we talk about the law of multiple proportions, okay, we look at nitrogen monoxide, which is a colorless gas that reacts readily with oxygen. When we show it diagrammatically, you see there's the yellow ball and the red ball. Its formula is NO. The mass of oxygen is 16. The mass of nitrogen is 14.01. So we're going to have do our multiple proportion, 16 over 14.01, and you get that proportion on the end. And nitrogen dioxide is a poisonous brown gas and smog. Notice it's nitrogen dioxide, so now there's 2 oxygens. Okay, so now your formula and then your mass of oxygen is doubled, and your mass of nitrogen, and we do the proportion, and we get 2.28 over 1. So we move on to Dalton's atomic theory, and Dalton basically would have stated that all matter is composed of extremely small particles called atoms. Okay, the word atom comes from an older word that basically means indivisible. So at the time of trying to understand how these matter is formed or put together, it seemed like theoretically if we could break matter down to the smallest, tiniest indivisible particle, then that's where we would start. And so the name was given to that particle, meaning smallest or indivisible, which was atom. Okay. Now we know, and we'll learn this, now that atoms actually are made up of smaller parts, but the name stuck. Atoms of a given element are identical in size, mass, and other properties. So every atom of oxygen is going to be identical. Every atom of gold is going to be identical. Every atom of silver is going to be identical. When we start looking at atoms of different elements, they're different in size, and they're different in mass, and they're different in other properties. So atoms of gold and atoms of silver are different from each other. And in Dalton's atomic theory, atoms could not be subdivided, created, or destroyed. Okay, again, we're talking about one of the earlier atomic theories. We understand now that's not entirely the case, but you need to apply this in terms of knowing what the theory said when the theory was developed. And then continuing, moving from atoms onto larger, talk about compounds and molecules, Dalton would state that atoms of different elements combine in simple whole number ratios to form chemical compounds. Okay, so we've got the basic understanding in terms of Dalton of the atom and what the atom is, and now this understanding that atoms can come together, and when they come together in simple whole number ratios and form chemical compounds. And then when we see chemical reactions, furthering Dalton's atomic theory, in chemical reactions, atoms are combined, separated, or rearranged. And that's what's happening in those chemical reactions, either a combining of atoms or a separating of atoms or a rearranging of atoms. Now, the modern atomic theory, in the modern atomic theory, there's a recognition that not all aspects of Dalton's atomic theory have proven to be correct. Okay, so he lays this theory out, and over time we recognize, some of these explanations aren't working, kind of like the stuff we heard about in that movie. First, we now know that atoms are divisible into even smaller particles. We also know that a given element can have atoms with different masses. But there are aspects of Dalton's theory that do hold up. Okay, we do know that all matter is composed of atoms, and we do know that atoms of any one element differ in properties from atoms of another element. So you can kind of see where his theory holds up and where his theory needed tweaking as time went on and knowledge increased. All right, guys, we're going to look at the next section now, and this is basically an overview of the structure of the atom. You're going to need to be able to summarize the observed properties of cathode rays that led to the discovery of the electron. You're going to need to be able to summarize the experiment carried out by Rutherford and his co-workers that led to the discovery of the nucleus. Be able to list the properties of protons, neutrons, and electrons, and be able to define the atom. Some of these things, guys, are really basically history lessons into the experimentation that took place in times past to give us the theory and the knowledge that we have now and our understanding of these things now. So you're going to want to be able to understand all of that. When we look at the structure of the atom, we know that the atom is the smallest particle of an element that retains the chemical properties of that element. We've already talked about that. And every atom has what we call a nucleus, which is a small region at the center of the atom. You can, if it's helpful for you to think of it this way, you can think of the nucleus of the atom the same way you think of the nucleus of a cell, if you've done cell biology. Don't get them confused. They are two different things. And don't use that analogy to then start thinking of an atom as a cell, because it's not. But it is a small region at the center. And in fact, it's pretty dense. It's dense because the nucleus has stuff in it. It's not just the center of the atom. The nucleus is made up of at least one positively charged particle called the proton, and usually one or more neutral particles called neutrons. Okay, and so one of the ways you can remember this guys, is P for positive for protons, okay, and N for neutral for neutrons. But the atom is not just that densely packed center. If, by definition, we're saying that this thing has a center, then we're also saying that it has a region outside of the center. And that is a region that surrounds the nucleus, and that region is occupied by the electrons. These electrons can be thought of as being in orbits. That was an older way of thinking of it. Now we think of them as in these energy shells. but the electrons are negatively charged particles. So you've got protons P positive charged, you've got neutrons N neutral, and you've got electrons being negative. And these three particles are referred to as the subatomic particles, meaning they are smaller or below or under the atom. They are subatomic. They're the particles that actually make up the atom. This chart here shows you the symbols that we use for each one, shows you the charge, shows you the mass number. Note that the mass number for electrons is 0. It's not really 0, right? By definition, if electron is a thing, it has to have mass. But we know that its mass is so small, especially compared to the other two, that we consider it to be negligible, and we do not include it in the calculation of the mass of any atom. Now, how was the electron discovered if it was so small? How was it discovered? And it was discovered through experiments using cathode rays in the 1800s, late 1800s. Rays that came out of cathodes were composed of negatively charged particles. And so that's how the electron was discovered, because all of a sudden now we're recognizing that there is something here that is connected to this matter that has a negative charge to it. And those particles were named electrons. And then going on, we have Joseph John Thomson's cathode ray tube. We're actually able to measure, in experiments he did with his cathode ray tube, he was able to measure the charge to mass ratio of electrons. And at the same time, or relatively at the same time, Millikan was doing oil drop experiments, which were able to measure the charge of electrons as well. And scientists were able to take the experimental data from all of that work and determine the mass of an electron. This diagram here shows you the cathode ray and the ray that would have been coming out of the cathode tube that would have had the negatively charged particles that were identified as electrons. Jumping ahead a little bit, early 1900s, 1911, the discovery of the atomic nucleus. This would have been Rutherford, Geiger, and Marsden were his associates. And what they did was what's known now as the classic gold foil experiment, which actually helped them discover the fact that there were these densely packed bundles of matter that had positive electric charges. And Rutherford called these positive bundles nuclei, or the nucleus. This diagram shows, or this picture shows, how that would have been done, with these positive particles being fired at a thin piece of gold foil. And many of those particles would have passed through and been recorded on the other side. But some of those particles would have deflected. One of the interesting things here to note, guys, is that one of the things that goes hand in hand with the theory of the atom is that matter is mostly empty space. If you've got a nucleus in the middle and you've got electrons floating around it and you've got space between the nucleus and the electrons, it's all mostly empty space. And if you shoot particles that are small enough, that are at the atomic level at something, many of those particles will actually pass right through. This principle actually is what drives X-rays. Right? But you did get, in the gold foil experiment, some of those particles bounced back or were sent off on these odd angles, which showed the experimenters that there had to be something there that they were hitting. Okay, so this is a diagrammatic explanation of what we just discussed, and you have this source for these positive particles were beamed, and you see most of the positive particles pass through. Okay, but you have a couple, some would have more of a wider angle of deflection, some would have a narrower angle of deflection. But regardless, they were deflecting, which meant they were deflecting off of something. And that something is what has come to be known as the nucleus. So, what is the nucleus made out of? Because it is the densest part of the atom, it must have stuff in it. And therefore, except for the nucleus of the simplest type of hydrogen, all atomic nuclei have protons and neutrons in them. A proton has a positive charge equal in magnitude to the negative charge of an electron. So what that means, guys, is that in most cases, the number of protons equals the number of electrons. Because in any atom, when the number of protons equals the number of electrons, you have an equal number of positive charge and negative charge, which means the overall charge of the atom is neutral. And this states this here. Atoms are electrically neutral because they contain equal numbers of protons and electrons. And a neutron does not play into this because a neutron is always electrically neutral. The other thing we know is that the nuclei of atoms of different elements differ in their number of protons and therefore in the amount of positive charge they possess. Okay? The atomic number, which is a number that can be found on any element on the periodic table, is the number that is associated with or corresponds to the number of protons. Every time you look at a different element, its atomic number is different because the number of protons is different. The number of protons in hydrogen is different from the number of protons in helium, so on and so forth. I tell you this to remember that the atomic number or the number of protons is ultimately what identifies what the element is. It is the identifying indicator, okay? And that's what this says here. The number of protons determines the atom's identity. Now we also know that there are forces within the nucleus. Two protons are extremely close to each other. There's a strong attraction between them. There's a same type of attraction when neutrons are close to each other, when protons and neutrons are close to each other. All of those attractions exist. And the proton-neutron forces that actually hold the nucleus together we call nuclear forces. We can also talk about size of atoms. Think about this. Every time your number of protons or your atomic number changes, it goes up, right? It doesn't go down, it goes up. And if the atomic number goes up, that means the number of protons has gone up, which means the number of electrons outside of the nucleus has gone up. So you're going to have an increasing of size in atoms as you work across the periodic table of the element. The radius of an atom is the distance from the center of the nucleus to the outer portion of its electron cloud. And it obviously, even though we're talking about these sizes increasing from one type of atom to another, it obviously is a very small number, okay, because atoms are very small. So this atomic radii that we talk about is small. And so we don't express atomic radii in units that we're used to. It's not expressed in kilometers or meters or centimeters. Or we have to express it in units that corresponds to the size of atoms to begin with. And that unit is the picometer or picometer. Again, that's the unit we use to express atomic radii. All right, guys, now we are going to look at the third section of the chapter here. And we're going to talk about isotopes and be able to define and explain what isotopes are, define atomic number and mass number, describe how they apply to isotopes, give the identity of a nuclide, determine its number of protons, neutrons, and electrons, and define mole, Avogadro's number, molar mass, state how all three are related, solve problems involving mass in grams, amount in moles, number of atoms of an element. In this section, this is it, guys. This is a lot of stuff I was talking about. You're going to take the stuff you learned about units, the stuff you learned about conversion factors, and now you need to memorize these concepts of mole, Avogadro's number, and molar mass. And going forward, every problem in chemistry can very well have all this information in it. Okay, we won't do gas type equations until week 6, 7, and 8 maybe, and even in gas equations you'll be talking about molar mass, Avogadro's number, number of atoms, so on and so forth. So you really got to nail this stuff this week. All right, the atomic number. Atoms of different elements have different numbers of protons. We've already covered that. Atoms of the same element all have the same number of protons. Oxygen will always have the same atomic number. It will always have the same number of protons. Okay, this is a principle in chemistry you're going to have to get down. Number of electrons can change. Number of neutrons can change, but the number of protons will always be the same. The atomic number of an element is the number of protons of each atom of that element. So atomic number and number of protons correspond to each other. So here we go. Here's oxygen. This is oxygen lifted off of the periodic table. The number above the chemical symbol is your atomic number. It is the number of protons in the nucleus. Okay. If it is normal, if everything is the way it's supposed to be, the atomic number will tell you the number of protons. The number of protons will always, unless you're told otherwise, will always equal the number of electrons. So if it's 8 protons, if it's oxygen, then unless you're told otherwise, it's going to be 8 electrons, and unless you're told otherwise, it's going to be 8 neutrons. Okay, so the atomic number will always tell you the number of protons. The number of neutrons and number of electrons can change, but there will be some other notation to let you know that they have changed. Okay, but the atomic number will always be the same. Now when we talk about isotopes, isotopes are atoms of the same element that have different masses. Okay, now let's think about this. The mass of any element or any atom is going to be a composite of the mass of the electrons, the mass of the protons, the mass of the neutrons. So if we're talking about atoms of the same element that have different masses, they must have a different number of something. Hope everybody follows this. The isotopes of a particular element all have the same number of protons and electrons, but different numbers of neutrons. So isotopes specifically refers to atoms of the same element with different number of neutrons. They obviously all have to have the same number of protons because they're the same element. And in this case, they have the same number of electrons, but the number of their neutrons is different. And in the real world, okay, not theoretically in a lab, but in the real world, most elements consist of a mixture of isotopes. So oxygen, what we report is what is the average or what is the normal, but there's going to be isotopes of oxygen that are out there. So on and so forth through all of them. Now what's the mass number? The mass number is the total number of protons and neutrons that make up the nucleus of an isotope. So you've got the atomic number. The atomic number is the total number of protons. The mass number is protons and neutrons. So I want you guys to start thinking math here. That if you are given the atomic number and you are given the mass number, you can figure out the number of neutrons. Because if the atomic number is the number of protons and the mass number is the number of protons and neutrons, you just subtract the atomic number from the mass number, and that will give you the number of neutrons all by itself. Let's see this again. So how do we designate isotopes? There is what we call hyphen notation. The mass number is written with a hyphen after the name of the element. So uranium-235. Okay. That's designating an isotope. Remember, it's the mass number here that's given. You've got to memorize the difference between the mass number and the atomic number and what they each represent. The nuclear symbol. The superscript indicates the mass number and the subscript indicates the atomic number. So when you're looking at a nuclear symbol, the superscript indicates the mass number and the subscript indicates the atomic number. That's going to look like this, okay? So you've got 235 is the superscript and that's the mass number. 92 is the subscript and that's the atomic number. The number of neutrons is found by subtracting the atomic number from the mass number. So I've already gone over this. I've already talked about this. If you memorize what the atomic number is made up of, and you memorize what the mass number is made up of, then what you have is the ability to determine protons and neutrons. Mass number minus atomic number equals number of neutrons. So 235 protons plus neutrons minus 92 protons, in our example of uranium, equals 143 neutrons. Nuclide is a general term for a specific isotope of an element. So when we talk about a nuclide, we're talking about a specific isotope of that element. So designating isotopes. Here's a sample problem. How would you do this? Or what kinds of questions would you be given? How many protons, electrons, and neutrons are there in an atom of chlorine 37? Now that's your isotope notation, so you know this is an isotope. What do? You're given the name and mass number, right? So that's the atomic mass number, 37. You've got to find the number of protons, the number of electrons, the number of neutrons. What do? Well, your atomic number equals the number of protons, which equals the number of electrons. Remember, protons and electrons are going to be equal unless you're told otherwise. Mass number equals number of neutrons plus the number of protons. We know the mass number is 37 minus the atomic number of chlorine equals the number of neutrons in chlorine 37. So how do you know the atomic number? You look it up on your periodic table. So you get 37 protons plus neutrons minus 17 protons equals 20 neutrons. An atom of chlorine 37, therefore, is made up of 17 electrons, 17 protons. How did we figure that out? Well, we looked up the atomic number. We know that the atomic number is 17. It will always be for chlorine, for any isotope of chlorine. We know, unless we're told otherwise, the number of electrons is going to equal the number of protons. So if the atomic number is 17, the number of protons is 17, which means the number of electrons is 17. And then we did our subtraction based on what we were given, and we're able to determine that the number of neutrons is 20. Now, what about the relative atomic masses of what we're talking about here? The standard used by scientists to compare units of atomic mass is the carbon-12 atom, okay, another isotope of carbon, which has been arbitrarily assigned a mass of exactly 12 atomic mass units, or 12 AMU. So what this means is that one atomic mass unit, or 1 AMU, is exactly 1/12 the mass of a carbon-12 atom. I hope you see that. If we assign carbon-12 12 AMUs, then that means 1 AMU is 1/12 of the mass of a carbon-12 atom. The atomic mass of any atom is determined by comparing it with the mass of the carbon-12 atom. So scientists have arbitrarily set carbon-12 as the standard, so all other atomic masses for all other atoms are going to be based on the standard that was set, being carbon-12. The average atomic masses of elements. The average atomic mass is the weighted average of the atomic masses of the naturally occurring isotopes of an element. Remember, we said that in real life, these elements exist as lots of different isotopes, okay? The average atomic mass is the weighted average of the atomic masses of the naturally occurring isotopes. How do we calculate the average atomic mass? The average atomic mass of an element depends on both the mass and the relative abundance of each of the element's isotopes. Okay, so if we're going to calculate the average atomic mass, we need to know the average atomic mass of the element, we need to know the mass, and we need to know the relative abundance of the isotopes. So, look at this. This is what one of these problems is going to look like. Copper consists of 69.15% copper-63, which has an atomic mass of 62.929601 AMUs, and 30.85% copper-65, which has an atomic mass of 64.927794 AMUs. The average atomic mass of copper can be calculated by multiplying the atomic mass of each isotope by its relative abundance in the decimal form and adding the results. So, (69.15%) becomes 0.6915 times 62.929601 AMUs plus 30.85% becomes 0.3085 times 64.927794 AMUs. When you do that, again, functionally, you do the multiplication first, then you add your two products, you get 63.55 AMUs as the average atomic mass of copper. So the calculated average atomic mass of naturally occurring copper is 63.55 AMUs. All this that we've talked about leads us up to the concept of the mole in chemistry, okay? And you need to know this concept. You need to understand it conceptually before you can do the problems with it properly. The mole is the SI unit for amount of substance. Note this, guys. We're not talking about anything other than the amount of substance. Mole, which is abbreviated MOL, you got to learn these abbreviations, is the amount of a substance that contains as many particles as there are atoms in exactly 12 grams of carbon-12. So we can mathematically figure out how many atoms there are in 12 grams of carbon-12. And because carbon-12 has become the mass standard for atomic mass units, if we figure out the number of atoms in a particular amount, being 12 grams of carbon-12, that number of atoms becomes standard as well, and that standard is a mole, okay? Avogadro's number, then, is 6.0221415 times 10 to the 23. What that is the number of particles in exactly 1 mole of a pure substance. This is always the same no matter what you're talking about. You got to understand this, okay? This is a constant. If you're talking about 1 mole of hydrogen gas, it means that there are 6.0221415 times 10 to the 23 atoms of hydrogen gas. If you talk about 1 mole of carbon, you are saying that there are 6.0221415 times 10 to the 23 atoms of carbon. If you talk about 1 mole of water, you are now saying that there are 6.0221415 times 10 to the 23 molecules of water. Right? There's no such thing as a matter of water, or I'm sorry, an atom of water. Molecules, right? So an Avogadro's number is the dozen of chemistry. What do I mean when I say that? Well, a dozen is a set amount. If you go buy a dozen donuts, we know that it's 12 donuts. If you go buy a dozen eggs, we know that it's 12 eggs. If you go buy a dozen ping pong balls, we know that it is 12 ping pong balls, right? You need to view and understand Avogadro's number the same way. If I were to tell you that you have a mole, okay, if you have a mole of Avogadro's number of ping pong balls, it means you have 6.0221415 times 10 to the 23 ping pong balls. So it's really, really important that you guys understand this so that you can apply it to the problems. How do you do molar mass? The mass of 1 mole of a pure substance is called the molar mass of that substance. Molar mass is usually written in units of grams per mole. So that tells you it's a derived unit. The molar mass of an element is numerically equal to the atomic mass of the element in atomic mass units. The molar mass of an element is numerically equal to the atomic mass of the element in atomic mass units. So we can actually do gram per mole conversions. Okay, so this is another layer of conversions. If you are given grams, you can convert to moles. If you are given moles, you can convert to grams. Because all of these constants, think about each constant that we have talked about that was set by scientists. It allows us, if I said you have 2 moles of carbon, you can actually convert that to grams. Right? If I say you've got 14 grams of hydrogen, you can actually convert that to moles. Now, I want you to understand why this is important. In a lab, you don't work in moles, you work in grams. But you can convert to moles. And this is where we start to do theoretical chemistry, because you can work the problem ahead of time on paper, show theoretically by converting moles to grams that when you do this reaction, you should get 1.82 grams of salt, or whatever, I'm using that as an example, then do the reaction and see if at the end you got 1.82 grams of salt. So molar mass is a conversion factor in chemical calculations. For example, the molar mass of helium is 4 grams per mole. What it is 4 grams of helium per mole of helium. To find how many grams of helium there are in 2 moles of helium, multiply by the molar mass. So 2 moles of helium times 4 grams of helium over 1 mole of helium equals 8 grams of helium. So you do the conversion, right? 2 moles of helium means that you have 8 grams of helium. So this, again, this becomes very, very important to the equations that you're going to be doing. Now, let's take that Avogadro's number and put that into these conversions. Avogadro's number can be used to find the number of atoms of an element from the amount in moles, or to find the amount of an element in moles from the number of atoms. So this takes our conversions all the way out to the next level. By using Avogadro's number, we can go from number of atoms all the way out to grams. In these calculations, Avogadro's number is expressed in units of atoms per mole. So we just showed you grams per mole, right? Now we're doing units of atoms, number of atoms per mole, which shows you how we can use these correspondingly to go from number of atoms all the way out to grams. So this chart, I've seen this before. If you're the type of person that can memorize this type of stuff, basically this can be helpful. It shows you how to convert, what your conversion is going to be to go from mass in grams to amount of element in moles, or to go from amount of element in moles to mass in grams, to go from mass of element in grams to number of atoms, to go from number of atoms to mass in grams, and to go from moles to number of atoms, to go from number of atoms to moles. These are all the conversion factors. If you memorize these, which you're going to need to do in terms of once you have problems on tests, If you memorize it this way, it may be very, very advantageous for you. Determining the mass from the amount in moles. Okay, how do you do this? Well, you have the amount. You're going to have to multiply in grams over mole to get mass. Or to go from the mass to the amount, okay, you go from multiply times mole over grams to get moles. Okay, this is all using molar mass as your conversion factor. Let's take a look at a sample problem. What is the mass in grams of 3.50 moles of the element copper? Well, how do you work this? First, what were you given? You were given 3.50 moles of copper. What you need to find is the mass of copper in grams. The mass of an element in grams can be calculated by multiplying the amount of the element in moles by the element's molar mass. So, moles of copper times grams of copper over moles of copper equals grams of copper. That's what that looks like formulaically. The molar mass of copper from the periodic table is rounded to 63.55 grams per mole. So you're either going to be given your molar mass in your equations or your problems, or you're going to have to look it up in your periodic table. Okay? So 3.50 moles of copper times 63.55 grams of copper over 1 mole of copper. Notice how you set this up so that you're getting rid of moles of copper, right? Just like the other unit conversions we did. You're left with grams of copper. You do your multiplication. You get 222 grams of copper. Another problem. A chemist produced 11.9 grams of aluminum. How many moles of aluminum were produced? What do you got? You're given 11.9 grams of aluminum. You need to figure out the amount of aluminum in moles. So, what does it look like? Grams of aluminum times moles of aluminum over grams of aluminum equals moles of aluminum. See, you're set. These are just like the other unit conversions you set up. The molar mass of aluminum from the periodic table is rounded to 26.98 grams per mole. Set up your problem. 11.9 grams of aluminum times 1 mole aluminum over 26.98 grams of aluminum. You're able to eliminate grams of aluminum. You do your math, which ultimately makes this a division problem. 11.9 divided by 26.98. You get 0.441 moles of aluminum. Another sample problem. How many moles of silver are in 3.01 times 10 to the 23 atoms of silver? Now what's this? Look at this, guys. You're given 3.01 times 10 to the 23 atoms of silver. You want to find the amount in moles. So, again, go to that chart I showed you, the triangle. How do you go from one to the other? Your silver atoms times your conversion factor is going to be moles of atoms over Avogadro's number of silver atoms equals moles of atoms. 3.01 times 10 to the 23 silver atoms, which is what you're given, times 1 mole of atoms over 6.022 times 10 to the 23 silver atoms, right? That's Avogadro's number. 1 mole of atoms will always be that number. When you do it, you can cross out silver atoms, and you can figure out by doing the division that you have 0.500 moles of silver. Now, guys, this could be a multiple step problem. It could have said figure out the amount of silver in grams, right? And so you would have had another conversion factor you would have put in, because you could go from number of atoms that you were given of silver, convert it to the mole of silver, which you had 0.5, and then do the other conversion to convert it to grams of silver. If you know atoms, then you can figure, if you know number of atoms, then you can figure out moles, and you can figure out grams. If you know number of moles, you can figure out number of atoms in grams. If you know grams, you can figure out number of atoms and moles. Guys, you're going to have to work these problems. These are basic, considered basic chemistry. Work the practice problems, and these types of problems should become second nature to you. Again, where you run into challenges during the week, you're not going to have as many practice problems this week, only the one lecture. Okay, where you run into challenges, ask me during the day. I've got plenty of board space. I got plenty of time while you guys are working on labs for you to work this stuff out. So please ask me, because I guarantee you these problems will be on your test. Okay. All right, guys, we're going to look at this one last problem, kind of put it all together. What is the mass in grams of 1.20 times 10 to the 8 atoms of copper? So this is the big kahuna of these types of problems. Yes, I said big kahuna. Deal with it. You're given 1.20 times 10 to the 8 atoms of copper. You want to find the mass of copper in grams. So now, here's a multi-step, right? You can do this all as one problem, or you can do it in multiple steps, but you have your atoms of copper times moles of copper over Avogadro's number of copper atoms times grams of copper over moles of copper equals grams of copper. You look up the molar mass of copper from the periodic table. You get 63.55 grams per mole. You start out 1.20 times 10 to the 8 copper atoms times 1 mole of copper over Avogadro's number. Copper atoms times 63.55 grams of copper over 1 mole of copper. You've set this up so that you can cross off, you can eliminate everything, right? Look, copper atoms on top, copper atoms on bottom. Cross them out. Moles of copper on top, moles of copper on bottom. Cross them out. The only thing you got left is grams. And you do the math, and you get 1.27 times 10 to the negative 14 grams of copper. Again, chemists, right? This is your theoretical. Theoretically, this is what you should get, and then you do the reaction, you do the experiment, and then you actually measure to see how close you got to theoretically what you should have gotten. Okay? Work hard this week, guys.